Alright, let's try this again with sound. Example 7.1 has someone pulling on like a shop vac, so it's something sitting on wheels. There may or may not be friction. In this case there's none, but it's still, let's do a free body diagram on it first. If I represent the mass, we're going to have a weight going down, mg, a normal force going up, and then we have some applied force, some F. This problem does not have friction. It could, but this is all we got. So we can break that force F up into x and y components, and they gave us the angle theta. So we can say the y component is F sine theta, and the x component is F cosine of theta. Alright, now they want to know how much work was done moving this mass through a distance or displacement of 3 meters. So we can go directly to our work is equal to our force times the cosine of the angle between it and the displacement times the displacement itself. You might see delta R, delta S, delta X, delta Y, all the same. So we have the magnitude of the force. It is a 50 Newton force. We have the angle, the cosine of 30 degrees. Unit circle tells me 30 degrees. The cosine is square root of 3 over 2. And we got to multiply that by the displacement, the 3 meters. Alright, when you crank that out, you get the work that has been done by the person pulling it on the mass, and we get 130 joules. Pretty easy. What happens if well, first let's take a look at this. We have some other forces that do no work. For instance, the normal force. There's no displacement. There is no delta y. Therefore, the normal force and the weight do no work. If it was moving up in space as well as horizontally through space, then we would also have to consider those terms. But the displacement was only in the x direction, therefore what we ended up doing was looking at the component of the force, F cosine theta, that is in the direction of the displacement, delta x. Okay, let's take this one step further. We also saw that we have a dot product definition. So if we look at example 7.3, it's a work done by a constant force still. Okay, they give us the displacement as 2I plus 3J, and that is in meters, and a constant force of 5I plus 2J, and that would be in newtons. They want us to calculate the work done on the particle by that force. So the work, by definition, would be equal to F dotted into dr. In this place, we're not going to have to integrate it from one position to another. We have the whole displacement, so we can just dot it directly into the displacement itself. So we get 2I plus, oh, wrong order. We get 5I plus 2J, this is newtons, dotted into 2I plus 3J, and that's in meters. So we're going to end up with a Newton meter. And how do we do dot products? We look at the like terms. So I get a 5 times 2 plus a 2 times 3. And that is equal to the work done. It's not a vector anymore. Remember that. It's just a scalar. And we end up getting a work equal to 16 joules. Remember, 1 joule is equal to 1 Newton meter is equal to 1 kilogram meters squared per second squared. So be able to go between those or recognize that we did proper unit analysis.